Hi, so let's look at this question here, which was taken from the year 2019 paper 1 question 11. I believe this question is on differential equation. Let's see if we can do this proficiently. Now, the first thing is, let's see try and draw a sketch or try and understand the question is talking about. So you're told that the scientists begin to investigate how hot water actually cools down, and the water is heated at a container and then placed at the room which is kept at a constant temperature of 16 degrees. Okay, so if this is a container, there's hot water inside. So there's a room temperature here, which is actually held constant at 16 degrees. Okay, so room temp is constant. Great, so we try and understand this. So then, after which the temperature of the water T after of water T minutes. So at T minutes, right, you know that it will be a function water temperature will just be theta Celsius. Okay, so that's one. Then the temperature decrease at a rate proportional to the difference between the temp. Okay, this is important. This sentence here is actually important. Okay, so let me just type out this sentence here, which and try and understand this. The temperature decreases at a rate proportional to the difference between the temperature of water and the temperature of the room. Let me just type this out. So this this sentence here would be the one which gives you the formula of the differential equation. The temperature decreases, so this temperature is decreasing, meaning to say this is d theta dt, right? Proportional meaning it's a fishy sign. The difference between the temperature of the water is theta, and the temperature of the room, which is held constant, which is at 16 degrees. Okay, so this is a pretty standard question, which you've seen it, and we've done it many times in lessons, during lessons. So this part here, what we do is actually just put d theta dt. This is the decreasing rate. So what we can do is actually just proportional. The temperature difference, obviously we want it absolute value. The water is obviously hotter, right? Because this is hot water. Okay, at theta degrees Celsius. So we will expect theta degrees Celsius to be more than the room temperature if it's a hot water. So we'll just put theta minus 16. This is what you could deduce, right? The rate of change of the temperature is actually proportional to the difference between the water and the temperature of the room. So what you can write here is d theta dt. Because it's a decreasing rate, you can put minus k theta 6, okay, where k is a positive constant. Okay, this is the first thing that we need. You must be able to write it out. Now once this is done, we're gonna proceed to see what else. The temperature of water fills from a value of 80 degrees. So from 80 degrees to 32 degrees. Okay, the time is in minutes, T minutes, right? T minutes. So at T equals to 0, you have theta equals to 180. Then after which at T equals 30 minutes, you have theta equals to 32 degrees. Okay, so let's see how we can solve this properly. This is a boundary condition. So this boundary condition will help you to solve the unknown which you'll find. Okay, so this case here, this is a separable form. Remember this part here. I think this is not really a difficult question per se. You have to be able to do this here in exam. So this d theta dt equals to minus k, after which we just integrate. This will be d theta minus 16 dt equals to minus k integral 1 dt. Okay, integrate k is fine as well. So this case here will be ln theta minus 16 equals to minus k t plus c. Make theta the subject, that will be easier. So theta minus 16 equals to e minus k t plus c, plus minus. Okay, so plus minus because it's modulus here. So this case here, what we're going to get is actually this is plus minus ec dot with e minus kt. A would just be plus minus ec. There you go. So this will be a E minus KT plus 16 theta. Alright. So I just leave it there. Then after which I'm just going to bring my boundary condition here. This boundary condition helps me a lot because when t equals to 0, so t equals to, when t equals to 0, we know that the temperature was 80 degrees at the very start. Alright, so this is important because once you use this to sub into this expression here, which is 80 degrees equals to A, E0 plus 16, you can actually solve your A straight away. So E0 is 1, A will be 80 minus 16. Okay, so this case here will be 64 degrees. Now when T is 30, we know that when T is 30 minutes, theta was 32 degrees. So just put into calculator here, this will be 32 equals to A, which is actually 64, and E, which is minus K, which is K, 30 plus 16. Okay, so now that I have my A is 64, right? So I'm just gonna replace 30 and so on into this expression here. So that's pretty okay. Once this is done, what we need is actually just solve for our K. Okay, so our K here will just be 32 minus 16 over 64 E minus 30K. So this is 32 minus 16 over 64, which is actually 1/4. After which we're just going to ln both sides, and this will be actually just okay, right? I'm just going to leave it as minus 30K equals to ln 1/4 here, and basically K 1 over 30 ln 1/4. Okay, great. So this is how you solve, because now you want theta. So theta is equals to, in an exact function of t, so in exact meaning to say we need this expression theta. So we have A is 64 and E minus K, so is plus 130 ln 1/4 plus 16. Okay, just replace all of it into this expression here, then you will get answer. Okay, so this is how you do this question here proficiently. Sorry, I made a mistake there. KT, so there's a T here. Okay, so there's a T here. Yeah, could you further simplify? Let me see. Yeah, this is okay. You can just leave it as such, exact. So I think the subsequent part is okay. For part B, find the temperature of the water after when time is equals to 45 minutes. So theta will just be 64, E minus 30. Actually, T could just simplify this to yeah, I'm just write this as theta equals to 64 E T over 30 ln 1/4. Okay, so this part here. B, what we do is actually just E 45 over 30. Did not want the exact value here. Did they want temperature of water after it's placed in the room? So we just can calculate 64 E to the power 45 over 30 multiplied with ln 1/4 plus 16. This will just be 24 Celsius. Okay, so that's how you do this part here. So let's look at part 2 of the question. Part 2 of the question, you're told that as the scientists now model the thickness of ice on a pond. In winter, the surface of water in the pond freezes. Once the thickness reaches, so let's say this is a pond. We are going to just, this is ice, right? This is ice here. Layer of ice. And this is the water pond in the water. So once, if it's the layer here is 3 cm, it's safe to skate. So 3 cm is safe to skate. The freezing of the water is modeled by a differential equation in which the rate of change of thickness of ice is inversely proportional to its thickness. Okay, maybe I type this out. The keyword here is rate of change of the thickness thickness. Rate of change. Change of the thickness of ice is inversely, these are the keywords, inversely proportional to its thickness. Okay, great. Okay, great. So this part here is important because we need to let the thickness. So let thickness at time, let's maybe let thickness at time t be x cm. Okay, so I'm just gonna let it be x cm at time t. That's the thickness. So to understand this phrase here, the rate of change of thickness, meaning to say this is dx dt, is inversely proportional to its thickness, meaning to say this is 1 over x. Okay, and it's an increasing function because in the winter, the what do you call it, the thickness of ice is increasing, right? So that is important. So once that's done, it's given that when t is 0, or t, did they give us t as a thickness of water? It's given that when t is at thickness is t. Thickness of a freezing water by the inversely proportional to thickness t. Okay, great. Well, let me check. Great. So they already labeled for us the thickness is actually capital T. So I'm just gonna let this be t instead of well, I let it be dt is actually proportional to 1 over dt. Okay, so that's pretty okay. Now once that's done, we are going to find you're told that at t equals to 0, at time t equals to 0, thickness would be 0. The thickness is 0 cm. T is in, small t is in minutes, after 60 minutes. Okay, can. So the small t is 60 minutes. Thickness becomes 1 cm. Now this is boundary condition, so this is also important. So once this is inversely proportional, just write this as dt equals to k 1 over t, 1 over big T. So where k is a positive constant. Okay, that's okay. So once this is done, this is a pretty okay question. This is t dt dt t. So this is integration of dt, capital T, k, small t, and this will give us t squared over 2 equals to k t plus c. So just bring down the so when t equals to 0, when small t equals to 0, capital T is actually 0. So this will render c to be 0. Is everything is just 0. So when t is 60 minutes, and t is actually in is 1 cm, right? So we could actually find our k here. So 1 over 2 equals to k times 60 plus 0. So k will just be 1 over 120. Okay, so find the time. Okay, great. So this case here, what we get is actually just t squared over 2 equals to k, which is 1 over 20. Remember, t is in minutes, okay? Because time t is in minutes. Because they gave you in minutes, right? So that's in minutes. So find the time when the freezing commences until when the freezing commences means from t equals to 0 until the ice is first safe to skate on. So safe to skate at t equals to 3 cm. Okay, so when t equals to 3 cm, with 3 squared over 2 equals to 1 over 20 t. So this will be t 9 over 2 times 120, which is actually 540 minutes. Okay, there you go. This is how you do this part here, meaning to say you need 540 minutes from the time it starts freezing, means t0. Okay, So this is how I do this questionnaire proficiently. Any question or comments, please do let us know. Keep practicing and I'll see you in the next question.